In Chapter 4, we're going to talk about different types of polygons, and 4.1 is with the talking about the parallelogram. So, first of all, let's introduce quadrilateral. Quadrilateral means a four-sided polygon. Polygon, of course, is a closed figure, and we're going to assume that this quadrilateral is on a single plane. In other words, if you were to draw it, it would be on sit on a flat piece of paper. Now there is another type of quadrilateral, and think of like a greeting card that has a fold. You would see part of the quadrilateral on one plane and part of the quadrilateral on another plane. That's considered a skew quadrilateral. We're not talking about that in this book. We're going to be talking about quadrilaterals that are all on one plane. And so now let's talk about parallelograms. A parallelogram is always a quadrilateral. So a parallelogram is always going to have four sides, and both pairs of opposite sides are parallel. So one set of sides is parallel and the other set of sides is parallel for a parallelogram. And that's actually the symbol for parallelogram. So a parallelogram is basically a subset of all the quadrilaterals, because a quadrilateral is any four-sided object. So that could be a quadrilateral, but a parallelogram is a special type of four-sided object that both pairs of opposite sides are parallel. And for our notation, we're going to mark a set of arrows like that. That shows that those two lines are parallel. And I'm going to mark that with two arrows there. That shows that those two are parallel. So that's how you would mark your diagram, showing parallel. So in this example, it says, given that we have parallelogram ABCD, and there's the diagonal segment AC, they want us to show that triangle ACD is parallel with triangle CAB. All right, I should probably draw that a little bit bigger for you. So here's vertex A, and here's vertex C, and here's vertex D, and here's vertex B. And what do we have marked here? We were told that this is a parallelogram. Okay, so parallel lines cut by a transversal, we're going to say that angle 2 and angle 1 are congruent. Angle 1 is congruent with angle 2. Why? Parallel lines cut by a transversal, alternate interior angles are congruent. Okay, we're also going to say that angle 3 is congruent with angle 4. And you'll see that this has two loops, and this also has two loops, and that is because parallel lines cut by a transversal are congruent. So angle 3 is congruent with angle 4. That's because parallel lines cut by a transversal, alternate interior angles are congruent. So that's an angle, and that's an angle. And of course, AC is congruent to itself. And that's the identity property, or it could be called the reflexive property, but there's a side. So there we can say that our two triangles, ACD, is congruent with CAB because of angle, side, angle. Angle, side, angle would be our reason. The one loop, the side, and the two loop. So we're going to name this one the one loop, the side, and the two looper. So here are some properties of parallelograms. Opposite angles. So non-consecutive are your opposite angles. If this is my parallelogram, these two angles are opposite. Opposite angles of a parallelogram are always congruent. Opposite sides of a parallelogram are always congruent. So these two sides will be congruent with each other. And the diagonals of a parallelogram always bisect each other. So there's one diagonal joining non-consecutive vertices, and there's another diagonal, and you can see that they don't meet at right angles, they bisect each other. So we have already seen the theorem. If two parallel lines are cut by a transversal, then the interior angles, same side, are supplementary. Let's continue with parallelograms here. What that's going to lead us to is two consecutive angles of a parallelogram are supplementary. So if this is my parallelogram, angle 1 and angle 2 are supplementary. Why? Because we have parallel lines cut by a transversal. These would be considered same side. They're on the same side of this transversal. Same side interior. So two consecutive angles of a parallelogram are supplementary. That would also mean that angles 2 and 3 are supplementary. And this is part of the definition of parallel lines. Parallel lines are everywhere equidistant. So this distance is the same as this distance is the same as this distance. They'll never intersect, so they never get closer to each other. Why is that going to be important? Because not only are we going to talk about angles and vertices of a parallelogram, and we have sides of a parallelogram, we're also going to talk about the altitude of a parallelogram. And we saw with the altitude of a triangle, an altitude is always perpendicular, stands straight up. It's considered the height. Well, the altitude of a parallelogram is a line segment drawn from one side perpendicular to a non-adjacent side. So that would be the altitude. Or you could draw the altitude here. It does not have to be from a vertex. Here, our altitude is from a vertex on the inside of the parallelogram. Here, our altitude is in the middle of the parallelogram. Here, our altitude is from a vertex, and it actually is drawn to the outside of the parallelogram. So the altitude is a perpendicular segment from one side to the opposite side, or the non-adjacent side. All right, so let's look at this figure. The definition of altitude is a perpendicular line from one side of a parallelogram to the non-adjacent other side. So notice here we're going left to right. We're not going up and down, but we are going from point M to point N, creating a right angle there. So that is a perpendicular line. So that could be considered an altitude too. All right, let's look at some inequality relationships for our parallelograms. So if two sides of one triangle are congruent to two sides of another triangle, and the measure of the included angle of the first side is greater than the measure of the included angle of the second side, This is going to be a long way to talk about diagonals of a parallelogram. Then the length of the side opposite the included angle is greater. So what is that saying? What that's saying is, actually we have a real good picture of it down here. Side BC is congruent with side EF because we have the two ticks. Side AB is congruent with side ED because we have the one tick. Okay, so here are two triangles where two different sides are congruent. But which angle is bigger? Obviously the angle in this first triangle is bigger, so that would mean the segment opposite that bigger angle is longer. The segment opposite the shorter angle, or the smaller angle, is shorter. And this is something we saw with triangles, that the largest angle always has the longest side opposite it. Well, the same is true here. If we had the same side lengths or congruent side lengths, which segment is longer? That's going to relate to the diagonals of a parallelogram. So if I have a parallelogram here, and this side is congruent with this side, and the side is congruent with this side, which is true for a parallelogram, which diagonal do you think is longer? That one? Or this one? Well, obviously the green line segment is longer. If we were to call this A, B, C, D, segment AC is longer than segment BD. Well, we would have known that because angle B is larger than angle A. That's really what that's getting to.